Okay, hopefully everybody is hearing my voice because I am speaking. This is a video with sound. This is on Chapter 2, Section 6, also known as 2.6, out of the Geometry Chapter 2 Study Guide. And this particular section can be kind of challenging. It really tests your skills by applying all the different postulates and properties that we learned in section 2.5. So all these properties that are algebraic properties, and these 5 properties that just talk about different types of symmetric property, reflexive property, transitive property, and then the 2 different types of addition postulates, the segment addition postulate and the angle addition postulate. All of these things are going to be applied in section 2.6. Now, the definitions. A proof is basically an argument, a written, logical, mathematical argument that starts with one given piece of information and then uses the rules and postulates and theorems and things that we already know are true to make conclusions based on what has already been stated. So we start with one thing and then we make statements that we know are true based on that, and then eventually we hope to conclude that something else is true based on all these things that we've developed that we know are true. So that's basically what a proof is. A lot of the proofs that we're going to be doing are 2-column proofs. We did several of those on the last lesson. I talked about how you have statements on one side, that's one column, and reasons on the other side, that's the other column. Not all proofs look like this. Some proofs are written just kind of as statements, one after the other after another, and those are called paragraph proofs. But like I said, most of the ones we'll do in 10th grade geometry here, or geometry, are going to look like this, the 2-column format. A theorem is basically a rule that we use, a statement that we already know is generally true, like a triangle has 3 sides, you know, that we can apply to help us make logical deductions and logical conclusions when we're making a proof. Okay. So this is the first proof. Basically this has been done for us. They just kind of deleted certain elements to it. As you can see, the first reason is blank. The first thing is always, there's going to be something that they give us that is true to start with. So for example, angle AXC is congruent to angle AXD. Oops, AXC and AXD. Those 2 are equal in measure. So we would say that that's part of the given information. And that's really all we have to state. If it's something that they already told us is true, then the reason is that it's been given. Now, angle AXD is actually these 2 angles put together, angle 1 and angle 2. So they're basically saying this part plus this part gives you the whole angle AXD. Angle addition postulate. And by the way, if these statements of reason over here are not making any sense, I suggest you go back to the video for section 2.5 because it's all slowly gone through and elaborated on in section 2.5. So from that section, hopefully you remember that the angle addition postulate basically says that one part of an angle, if you add the other part of an angle, the 2 parts should give you the total. Angle 1 plus angle 2 gives you angle AXD. This is a D right here. That's a C. Okay. Angle AXC is the combination of angles 3 and 4 for the same reason. The part plus the part gives you the total. This is angle AXC. Now what they did is they said that the measure of angle 1 plus angle 2 equals the measure of angle 3 plus angle 4. So what they basically did is they took the original statement of equality, that angle AXC is equal to angle AXD, and here they gave it a new name. Angle AXD is the same as angle 1 plus angle 2. angle AXC is the same as angle 3 plus angle 4. So this statement, they actually wrote it the other way around. This one says measure of angle 1 plus angle 2 is equal to measure of angle 3 plus angle 4. So it's actually substitution. They took the original equation and they took out these names and they put in those names. So step number 4 is the substitution property. Because it's this equation just with new names for what these sides could be. Okay, now the left side here on number 4 has a measure of angle 2 in it, and the right side has the measure of angle 3 in it. Well, what did they do? Well, it seems like they removed angle 1 and angle 4. Do you see that? Well, they gave a statement that measure of angle 2 is equal to measure of angle 3. But here's the weird part. This doesn't have actually anything to do directly with that. A lot of times our logical statements flow directly from the thing above, but sometimes we just start with a new idea. And so this is not connected directly to this. Where did this come from then? Well, if you look on the page, you might be able to see that the measure of angle 2 being exactly the same as the measure of angle 3 is actually part of the given. And we can use these anytime we want. We don't have to prove them true. Given information, a lot of times we just throw it all in at the beginning, but sometimes we need to kind of use a piece at a time. We really only needed to use this one piece if we wanted to make this logical sequence happen, but then using this piece at this time, you can see that we are going back, we're grabbing this and we're restating it. And the reason why we can restate it is that we know that the measure of angle 2 and angle 3 are the same exact thing. So instead of calling this the measure of angle 2, instead we're going to give it its other name. 2 and 3, same thing. So I'm going to substitute out the measure of angle 2 and put in the measure of angle 3. You can see that's the substitution property. Something was taken out and something else was added in. Okay, so 4 and 6 are kind of the same step, it's just that we're doing a substitution based on this given information. So the final step is a logical connection. Step 6 does flow nicely into step 7. How do we get from step 6 to step 7? Well, the left side has the measure of angle 1, but the measure of angle 3 is gone. The right side has the measure of angle 4, but the measure of angle 3 is gone. So it looks like the measure of angle 3 would just kind of disappeared from both sides. So can we do that on an equation? Can we take one side and the other side and take away the same element? Yeah, that is called the substitution, or excuse me, subtraction, what I'm trying to say, subtraction property. On any equation, we can subtract the same thing on both sides. So even though it's not written this way, basically step number 6, measure of angle 1 plus measure of angle 3, this is step 6, equals measure of angle 3 plus measure of angle 2. Basically what they did is they just subtracted the measure of angle 3 on both sides, and they ended up with step 7 being just this equals that. That is subtraction. Oh, not on the screen. Sorry. There you go. So this is just my elaborated version of step 6 and 7, just to show you kind of what happened. Written out lengthwise horizontally instead of smushed up there. Okay. So these 3 properties are going to be really important to know. This is just a review of the reflexive, symmetric, and transitive properties that I talked about yesterday. Actually wrote all these the same kind of thing yesterday, but just to review, The reflexive property simply says that something is always going to be the same as itself. So the line segment AB will always have the same length as itself. If line segment AB is congruent to line segment CD, symmetry, so the symmetric property basically says that you can make that statement in the opposite order, that line segment CD would be congruent to line segment AB. Symmetric property just flips it around in order. And then the transitive property has two statements. If segment AB is congruent to segment CD and segment CD is congruent to segment EF, then because this CD is an element that exists in both of these statements, then I can go from the original hypothesis to the final conclusion, kind of, by saying then AB would be congruent to EF. This is the one that I said was like the law of syllogism, where you kind of have an original statement, then you have a second statement, and you're able to link, because of the common element, the initial statement with the final conclusion. But when we're doing proofs, we call it the transitive property. And then you can do the same thing with angles. The measure of angle A is always going to be equal to itself. That's the reflexive property. Symmetric property says if angle A is congruent to angle B, then angle B is congruent to angle A. The symmetric property flips the order. And the transitive property says if angle A is congruent to angle B and angle B is congruent to angle C, then angle A must be congruent to angle C. Because of the common element, you can start with the original statement and then skip to the final congruence with C. So, which one of the statements is shown here? If angle 5 is congruent to angle 3, then angle 3 is congruent to angle 5. Well, it seems like what they've done is they've flipped the order. 5 is congruent with 3, then 3 is congruent with 5. The property that flips the order is the symmetric property. All right. Well, let's see if we can apply at least one of these rules that we've been reviewing here to the next proof. Well, it turns out that we're not going to use any of these three properties in this proof, but there will be one of the other ones that we learned in section 2.5, two of them actually, that we'll use. So, okay, so here's my entire line segment AC. That's our whole piece, the total amount. And AB is this part over here, and BC is that part over there. So what I see when I look at this is they're saying that AB, this part, if you add that to the other part, BC, that gives you the whole thing, AC. So when you have a statement that part plus part equals total, that is an addition postulate, not the addition property, the addition postulate. And since these are line segments, the official name is the segment addition postulate, is the reason that we can state that two parts add up to a total. And then here, it looks like line 2 and line 3 are the same except for this last thing. They took out BC and they put in AB. And that would be, we can do that because it's already stated that those two things are the same. And you can always use substitution when two things are the same to just give it the other name. So the final reason would be substitution property. So this is basically what you should focus on first. Just focus on figuring out what the reasons are and how they're used. And then eventually you can work with creating a proof just starting with the given and the diagram. Okay. So going back to the properties we talked about at the top of the page, the reflexive property, something's the same as itself. Symmetric property, if you flip the order around, it's the same. And transitive property, meaning if A equals B and B equals C, then A must equal C, that kind of thing right here. So which one is this one? If angle H is congruent to angle T and angle T is congruent to angle B, then angle H would have to be congruent to angle B. Well, like this, the law of syllogism, we were able to jump from the original statement to the final statement, and that would be the transitive property. Okay. So we have several proofs that we have for examples here. And the first one, as you can see, doesn't really give us anything over here. We kind of have to do this from scratch. So what do I know for sure to start off with? I know that BD cuts angle ABC in half. That's what bisects means. Bi means two, sect means cut. So if BD, this ray BD, cuts this whole angle in two equal pieces, that's what the given means. So we always start with what we've been given, and then we try to make logical conclusions from that, make other statements of truth that flow from that. So we write the statement on the left, and then the reason being it was given to us already. Okay, so what I want to do is I want to prove that doubling angle 1 gives you the entire thing. Well, what I know is that with the angle addition postulate, I can add angles 1 and 2 and I get the whole thing. So maybe I'll start with that. 2. The measure of angle 1 plus the measure of angle 2 gives you the measure of angle ABC. And that would be because of the angle addition postulate. Okay. Well, what else do I know about this diagram? Well, I know that if this line cuts this full angle in half into two equal pieces, can't I say that angle 1 and angle 2 are the same? Yeah. That's what half means, is the two pieces are the same as each other. So I'm going to say that the measure of angle 1 equals the measure of angle 2 because because we had an angle bisector up here. So I'm going to say because of the definition of an angle bisector. So we've never given this type of reason before. It's called a definition. So when you basically are referring back to some other statement of truth, like a bisecting component or a 90-degree angle that's, you know, a right angle, or, you know, you want to, if you know it's 90 degrees and you can state it's a right angle or vice versa. Basically anything that's before that's not like an obvious rule, if it's just a statement that you know that this bisects it and therefore the two pieces would have to be equal. A lot of times that's just going to be a statement of truth. Hey, I know this is true, therefore that's true. So because this is a bisector, because of the definition of an angle bisector, then these two must be equal in measure. Okay, so what else do we know? Well, I'm going to say that eventually I want to get the measure of angle 1 added to itself, because that would be the same as twice the measure of angle 1, right? Measure of angle 1 plus measure of angle 1 equals double that. So if I could somehow get to the point where I'm saying measure of angle 1 plus the measure of angle 1 equals measure of angle ABC, that would be great. Now, if you can see on line 2, I almost have that. Here I have the measure of angle 1 plus the measure of angle 2 equals the whole thing. If I could somehow get rid of this and state measure of angle 1, then I would have, I'm almost there. Now I can do that because line 3 says that the measure of angle 1 and the measure of angle 2 are the same. So when two things are the same, we can always substitute one in for the other. So you can see here I took out the measure of angle 2. In its place I put the measure of angle 1 because of the statement of equality that I made in step 3. So that's basically the substitution property. It says I can do that. And then finally step 5 is when I multiply measure of angle 1 by 2, it's the same as adding it to itself. That's what they wanted us to prove. Up here I'm just writing it in the opposite order. And I'm just going to write that I did a simplification. Simplified by adding like terms. This one, what's the reason that we always give first? Well, we state the given first. Definition of congruent segments. Well, basically that means that if line segment AB is congruent to line segment CD, then the measures must be equal. So you can see these two are almost the same. This is a statement of measure or length, whereas this is just the name for the segment. So we can kind of go back and forth. If we know that two things are congruent, we can say that they're equal measure, or if we know that they have equal measure, we can state that they're congruent. We can go back and forth between these statements depending on what kinds of statements do we want to make. Do we want to make a statement of congruence and just use the names, or do we want to use lengths? And that's kind of where they're going with this one. Symmetric property, what does the symmetric property do? It flips the order of things. So if this was my last statement, I'm assuming that this was their second statement, that CD was equal to AB, because that's what the symmetric property does. It just takes a statement and flips it. And then finally, as you can see, I went from a statement of equal measure to a statement of segment congruence. This and this, you can do this in any order. If this is true, that's true, and if that's true, this is true. So there you have it. Again, we're using the definition of something to make a statement of truth. In this case, for congruent segments. All right. On the next page, you have this triangle. And it says that HI, this segment right here, is 9 units long. So I'm going to mark that, 9. It says that IJ is also 9 units long. And it says that IJ is congruent in length to JH. Okay. So I usually like to state all the givens at once, but on this one I'm just going to start with let's see. Let's do HI is equal to IJ. Now, this is actually given to me since 9 equals 9. And so from that, I can conclude that line segment HI is congruent to line segment IJ because of the definition of congruent segments. I'm going to pull in a given. What I'm trying to do is get to the point where HI and IJ are JH are linked together, and if I can prove that something else is true, because basically the transitive property says, it has 3 elements. The transitive property says that if you can prove 2 things are congruent and then one of those things is congruent with something else, then all three elements will have to be congruent. So that's kind of where I'm going here. I know that the top side and this side are congruent. Now if I could state that one of these two is congruent to hj, then I could conclude that all three of them must be the same. So back up here in the given, they're telling me that ij is congruent to jh, and that was given to me. So you can see here that hi, the top, is congruent to ij, the right side. And then here from the given, I've been able to state that ij, the right side, is congruent to jh, the left side. So I should be able, by the transitive property, to jump from the original to the final conclusion. So I should be able to say that hi is congruent to jh because of the transitive property. This one is very, very similar to this one. This property is basically the same as this, but with midpoints. So for that reason, I'm not going to put it in this video. But you can get these notes from your teacher if you really want the hard copy of what we did in class. You could get this, and this one over here as well that I did not cover.